In this video, we will use collision theory to understand how certain factors affect the rate or speed of a reaction. Specifically, we will investigate how the rate of a reaction is affected by changing concentration, pressure, or surface area. Let's start by briefly recapping what collision theory says. The rate of a chemical reaction is often understood by collision theory. Collision theory says that the reacting particles, whether atoms, molecules, or ions, need to collide with each other to react, and that not all collisions result in a reaction. They need to possess a minimum amount of energy when they collide to react with each other, and this minimum amount of energy is called the activation energy. And thirdly, particles need to be orientated or positioned in a suitable way that will promote a reaction. In the three diagrams, all the particles are undergoing a collision. In the first diagram, the particles are correctly orientated, but in the second and third, they are not. If the particles in the diagram do not collide with enough energy, they will not react. If they do collide with the minimum amount of necessary energy, the activation energy, bonds will break and new bonds will form. We call this an effective collision. An effective collision is a collision which results in a reaction, because all three requirements for a reaction were fulfilled. Now that we have recapped what collision theory is, let's have a look at factors which affect the rate of a chemical reaction. There are 5 main factors which affect the rate or speed of a reaction: the temperature of the reacting species, the concentration of the reactants, which we usually use for reactants in solution reacting with each other, the pressure of the reactants, which we usually talk about when gases react with each other, surface area, which we talk about when one of the reactants is in a solid state, and catalysts. It is important to note that the rate or speed of a reaction depends on the frequency of collisions. Frequency of collisions is not the same as the number of collisions. The frequency of collisions is the number of collisions per unit time, and we usually say per second. So when we talk about factors increasing or decreasing the reaction rate, we talk about the frequency of the collisions being affected, not the number of collisions being affected. In this video, we will focus on how concentration, pressure, and surface area affect the frequency of collisions and thus the rate of a reaction. Before we look in depth, let's quickly mention how temperature and catalysts affect the rate of a reaction. For temperature is proportional to kinetic energy. The higher the temperature of the reacting particles, the more kinetic energy they possess, the faster they move, and the more vigorous the collisions will be. This will increase the frequency of collisions, which in turn will increase the number of effective collisions, which will increase the reaction rate or make the reaction go faster. Let's have a look at catalysts in brief. The presence of a suitable catalyst decreases the activation energy needed for a reaction, so aids in increasing the number of effective collisions, and thereby increases the speed of a reaction. Now, we very briefly discussed temperature and catalyst, but let's hone in on the focus of this lesson: concentration, pressure, and surface area. We'll start with concentration. Changing the concentration of reactants affects how fast a reaction occurs. Concentration can be defined in several ways. It is the amount of a substance, usually referred to as the solute, in a given volume of solvent, solution, or space. Let's consider a low concentration and a high concentration of solute particles in liquid. When we discuss pressure just now, we will consider the amount of substance in a given space, and here we will just look at solutions. So we have simplified our definition of concentration. For a low concentration, there is a small amount of solute relative to the overall volume of the solvent or solution. For a high concentration, there is a large amount of solute relative to the overall volume of solvent or solution. Now, particles in solution are always moving randomly. For a low concentration solution, there is a low frequency of collision. Only some of these will result in an effective collision to produce the product. Here the product has been drawn with solid balls so that we can identify it easily. So the frequency of effective collisions in a low concentration solution is low, and this causes the reaction rate to be slow. In a high concentration solution, however, because there are more particles in the solution, they are closer together and have a higher probability of colliding as they move randomly. There is a relatively higher frequency of collision. Some of these collisions will be effective, and so there is a relatively higher frequency of effective collision, and this leads to a relatively higher reaction rate. We can summarize all of this by saying, increasing the concentration of the reacting substances in a solution increases the rate of the reaction. Now let's have a look at how changing the pressure affects the rate of a reaction. When we talk about pressure and reaction rates, we are usually referring to gas particles specifically. The proper definition for pressure is related to the force per unit area that gases exert on a surface. But we can think of it as being similar to concentration. In other words, the amount of gas particles in a given volume of space. If we take the same number of reacting gas particles in two different sized containers, one with a large volume and one with a smaller volume, the pressure of gas particles in the large volumed container would be low, and the pressure of gas particles in the smaller volumed container would be relatively higher. Again, this is because there is the same amount of gas particles in each vessel, but each container has a different volume. In the first diagram, there is a lower density of gas particles. They have more space to move. And in the second diagram, the gas particles are more densely packed with less space to move. Particles are continually moving randomly, and some will collide. In the low-pressure system, there will be a low frequency of collision, with only some of these particles effectively colliding, as shown by the solid circles. In other words, the low pressure resulted in a slow reaction rate. For the small volumed container with the same amount of particles, there would be a relatively higher frequency of collision. The particles are more likely to bump into each other because of the reduced volume in which they can move. Some of these collisions will result in effective collisions. And at this higher pressure, there is a relatively higher frequency of effective collision, which means a faster or higher reaction rate. To summarize all of this, the higher the pressure, the faster a reaction occurs. If we take the stripy black object at the top of the diagram to be a piston, and it is pushed down to end up with the small volume in diagram 2, the pressure will increase. This specific action of increasing pressure will speed up the reaction. A specific example of a real-life situation where a high pressure of gases is not desirable but actually hazardous is in the mining industry. When methane gas levels, or in other words the pressure of methane in mines, gets to a certain level, the methane can ignite if there is a heat source available and even explode. This poses a real danger to miners. And so the pressure of methane, or we could call it the concentration of methane, must be carefully monitored to ensure the safety of the workers. We now know about how changing the concentration or changing the pressure can affect the rate of a reaction. What about changing the surface area of a solid reactant? Ever wondered why kindling burns so much quicker than big logs of wood? Besides dryness and flammable oils in the kindling and wood, the answer is surface area. Kindling has a large surface area exposed to atmospheric oxygen, which means it will burn much quicker than a piece of wood as it reacts with oxygen in the air. Surface area could be defined as the total area of all the surfaces of a solid. Taking a cube for simplicity's sake, the surface area would be 6 multiplied by the length times the breadth of each side. We use the number 6 because there are 6 sides to a cube. So let's imagine this cube is a piece of metal that's going to react with oxygen in the air. Let's make the length 4 units long and the breadth 4 units long because this is a cube. We get 6 multiplied by 4 times 4, which gives a total surface area of 96 units squared for this cube. Imagine we then chopped up our piece of metal into smaller pieces, as shown in the diagram. We'd end up with 4 smaller cubes from the top layer and 4 smaller cubes from the bottom layer. The length and breadth of each side of each of the small cubes would be 2 units. Then if we worked out the total surface area of all 8 smaller cubes, we'd get 8 because there are 8 cubes, multiplied by 6 for the 6 sides of each cube, in parenthesis multiplied by 2 for the length and breadth of the sides of each cube, which gives a total surface area for all 8 cubes together of 192 units squared. By cutting our metal cube into smaller pieces, we have greatly increased the surface area. In other words, smaller pieces of the same volume give a larger surface area. Let's check the total volume is the same for both. We can calculate the volume for the big cube by using length times breadth times height, and do the same for the smaller cubes, except this time multiplied by 8 because there are 8 little cubes in total. For the big cube, we get 4 times 4 times 4, and the little cubes 2 times 2 times 2 times 8. And we get the same final volume for both calculations. This makes sense. We did not lose any of our original metal, nor did we add to it. We merely cut up our big piece into smaller pieces. So we can adjust what was written here to say smaller pieces of the same total volume give a larger surface area. But how does all of this affect the rate of a reaction? Taking our same piece of metal again, if we were to cut it in half and open it up, if we ignored the front half and had a closer look at the back half, we'd be able to distinguish between surface particles in orange and inner particles in blue. The surface particles are all exposed and are available to quickly and easily react with other particles that come into contact with them. For example, oxygen molecules in the air interacting with the metal surface particles. The inner particles are temporarily unavailable to react while they are still covered with surface particles. And so the reaction rate depends mainly on those particles which are exposed and available to react. So it makes sense that smaller pieces of a material give a larger surface area, and thus more surface particles are exposed to interact with another reactant. And this in turn gives a faster reaction rate. To summarize all of this, increasing the surface area of a solid by breaking or cutting a solid into smaller pieces increases the rate of a reaction. In real life, not all solid reactants come as nice neat cubes or can be cut into nice neat cubes like metals can. For example, sulfur, when it's stored in a container, often forms big chunky lumps. These big lumps have a low surface area. By grinding up the lumps using a pestle and mortar, the solid can be powdered. The very small pieces of powder have a very large total surface area, which is perfect for performing a fast reaction. It is important to note that changing the surface area of a lumpy compound does not affect the energy with which a reaction occurs, but only the rate at which it occurs. A real-life example of a potential hazard from a substance with a very high surface area is the fine airborne powders released into the air from flour mills. These particles are so small and have a very large surface area. If they become overheated or electrostatically charged, these particles can undergo a fast reaction with oxygen in the air. They may ignite and may even cause explosions. Let's summarize everything we have learnt. We learnt that factors which influence the rate or speed of a reaction include temperature, concentration, pressure, surface area, and catalysts. Specifically, we investigated concentration, pressure, and surface area in some depth. We saw that increasing the concentration of a solute in a solution, or increasing the pressure of gases in a vessel, or increasing the surface area of a solid reactant by breaking it into smaller pieces, increases the frequency of collisions, in other words, the number of reactant particles that collide per second, which in turn increases the frequency of effective collisions, in other words, the number of successful collisions which result in a reaction per second. And this leads to an increased rate of reaction, in other words, a faster reaction. Similarly, decreasing concentration, pressure, or surface area leads to a decrease in the rate or speed of a reaction.